a couple more minutes. Hopefully we'll like this room a little bit better than the other room. The tables are, I think, a little more convenient. Everybody get a white syllabus? All right. Well, it's time to go. Everybody got a green? And everybody got a blue? Okay, 3 handouts today. Let's look at the syllabus, Organic 2. Here's your cool stuff. It is pretty cool stuff. Cool stuff is like Dutch for carbon, right? There we go. Everything's on the first page. In terms of textbooks, the official textbook is a book by Klein. This is a hardback. There's a paperback version in the bookstore. As I've mentioned, Organic 1. It is okay to use any textbook you want. Just about any organic textbook got the same topics. Okay. You can use the index to find what we're covering. So if you want to save a little money, I understand that. But this is the official textbook of the course. Okay. Topic chapters are listed on the daily outline, the second page of the syllabus on the back. But you have an index. You know what we're covering. I give you handouts. Use the index to find what we're covering in your book. I recommend a solutions manual to your textbook. This is the one hardback for Klein. If you buy the one in the bookstore, I think it comes with an online code. That online code gets you the free solutions manual. Okay? If I'm incorrect, please let me know, but I think that's what we have in the bookstore. You need a lab techniques book. This is the one, it's on the syllabus, one by Morag. This may be an older version, blue or burgundy. You can also use the one by Zubrick. We used to use that one many years ago. You get one for a penny on Amazon. Basically, do you need any of this? No. What you need to do is be successful in the course. Okay. But if you're not reading about lab techniques before you come to lab, then you're not going to be able to do well in lab. Okay. I don't require you to do something. You want to do well in the course. Whatever's good for you. These are the recommendations. Also have a workbook lab manual. This is pretty much required because they have lots of information about lab. There's a table of contents. Please read the table of contents. Every semester students are like, I didn't know that was in the workbook. Well, here it is in the table of contents. In here you will find all of our labs, including information for checking in, which you'll be doing this week. So you need this to check in. Lab report requirements, lab notebook requirements, safety guidelines, directions for using the IRs, melting points, and the rotovaps. Washing glassware in the lab. I think that's new to the workbook. I don't think I had that in Organic 1. Basically stuff that's in the workbook I expect you to know and be familiar with. The guidelines, I mean, at some point it says you can't have the lab handout in lab. It doesn't mean you can't have the instructions, like how to use the IR, how to use the rotovap, etc. Basically, you can't be referring from the lab as you do the lab, because you have to have a pre-lab, which shows that you have prepared to do the lab. Basically, all this is spelled out in the lab guidelines. Please read. course, if you have me for Organic 1, similar setup. There are questions for each test that I have put together. Most of them are my own. Multiple choice questions, etc., etc. The final exam in this class is multiple choice, ACS exam, 70 multiple choice questions covering Organic 1 and 2. All this is in the syllabus though. Video lectures will be recorded, posted on YouTube. If you have any trouble getting there, let me know. I'm not going to read this stuff to you guys. We need to get moving. Second page, I give you some tidbits. Third page, tidbits about studying. In summary, a few things. You need to be organized. Okay, there's lots of material in Organic 2. It's not so much difficult. It's just a lot of material. Okay, if you can keep everything organized, it's just going to help you learn it so much easier. Okay, very organized. Please make note of various things in here. General policies, academic honesty, reading and following directions. Office hour requirements. Okay. Back of the second page is the daily outline, just like you were getting one if you had me. This is what we're doing today. We're going to start with alcohols, chapter 13, nomenclature, some reactions of alcohols. And then over here is your lab, either Thursday or Friday. This week what are we doing? Lab check-in and then NMR lecture. You'll probably be downstairs in a room over in Science Hall. Please be prepared to check in. Brief overview of Organic 2. First test is alcohols, ethers in general, and NMR. NMR is the most important of the organic spectroscopies. It's also the most extensive. Test 2 is generally aromatic chemistry. Benzene, reactions of aromatics, huge area of chemistry. Large number of drugs contain aromatic rings, benzene ring being the sort of the granddaddy. Here's some drugs here. You see all these drugs contain an aromatic benzene ring. Most of these you're familiar with. Tests 3 and 4, carbonyl chemistry. Carbonyl chemistry, very important, especially when you go on to like biochem. Test 3 is your acid derivatives like carboxylic acids, esters, amides. And then test 4 is aldehydes and ketones. But there is a lot there. Majority of what we do, we'll use the foundation from Organic 1, mechanistic foundation, both the alkene type reactions and the substitution elimination reactions. That's your foundation. Okay, we'll apply that a lot, especially during test 1. There's a lot of review of the alcohols and ethers. We'll use that foundation and we'll build upon it as we go on tests throughout. We'll learn a few new fundamental things, but if you didn't do well in Organic 1, you're already kind of behind here. You've got to freshen up on your Organic 1. Acid-base chemistry, etc., etc. You might want to get a job one day. I think I gave you this in Organic 1. Basically, if you read right here what this job requires, this is old, but there's lots of these current. It requires experience with multi-step organic synthesis. We will be doing more multi-step synthesis. Okay, we did very little bit of that, if at all, in Organic 1 with me. Purification of organic compounds. Hopefully, you'll be doing that in lab. Must have an understanding of fundamental reaction mechanisms. Okay, sort of the basics of what I try to teach you. Functional group reactivity. Organic 2 is largely looking at the chemistry of various functional groups. Chemistry of aldehydes, chemistry of amines. Familiarity with spectroscopy techniques including NMR, IR, mass spec, etc., spectral interpretation. So in the end, this stuff can help you get a job if you want to get a job in chemistry, and drug companies take care of their employees very well, good pay, gourmet buffets, daycare on site, weight rooms on site, you know. What else is here? I put this in, this is kind of new to my syllabus packet. Basically, there's more to life than just taking tests. Your day-to-day work, you're being observed, okay? Ultimately, a number of you ask for faculty recommendations, okay? To me, very little comes from your performance on test. You know, that's a wee little bit. This is more of it here. Take a look at some of this, think about this. You know, Santa Claus is always watching. So think about how you're evaluated and how, you know, faculty or potential employers are evaluating you. Okay? And every day, you know, when you interact with, you know, senior people, faculty, etc. So keep that in mind. That's from what, Eastman Chemical Company. In the back, I always give this. Anybody interested in selling organic tube? Okay, if you are, here you go. Here's how you do it. I recommend you do it. Okay, a little bit of this, obviously sarcastic. Please read this, and obviously don't do this stuff, okay? All right? That's the syllabus. If you have any questions, please ask first thing on Wednesday, okay? Please read. Here's the workbook lab manual, organic tube, available in the chemistry and physics office, not in the bookstore. ChemPhys office, $15 cash. I hope you'll find this to be a convenience and something valuable to you. Again, organization, okay? I've attempted to sort of organize stuff for you to a degree, but you have to be organized with your stuff as well. Okay. What have we not talked about? Questions at this point? Not from the syllabus, but just anything else. Question?
Is there any point in time that we can see our final from organic one?
Just stop by. Okay, let's get started. Chemistry of alcohols and ethers. Blue is going to be our outline. Give sort of warm-ups. Warm-ups may be very straightforward, but very often they're sort of advanced. Give you some interesting questions that you may not be able to answer right now, but we'll try to get you going, get you thinking, and go to the textbook, seek out the answer, what's going on here. Application. Lincomycin can be converted to clindamycin. What's the difference in the drugs, etc. On the back, another warm-up. Basically try to show you why some of the chemistry is important that we're going to be doing. Okay? I don't want to take 10 minutes here and explain why chemistry is important. Okay? We need to be looking at the chemistry. Because time is limited. You want to see how to work problems in the material. Okay? But you do need to know why this stuff is important. And so when you read the chapter, get a little feel for why it's important. And I guarantee you, you know, your organic 1 and organic 2 is going to be very valuable to you as you proceed in a career in science. Okay? Hugely applicable, very practical, and I try to be very practical. I don't like to teach you stuff that's just, let's just learn this for what, okay? If you ever have a feeling, why we learn this, please raise your hand and say, why is this important, okay? Well, nomenclatures of alcohols and ethers. You've got to be able to have some terminology to name them and talk about them. And so that's where we're going to start. Okay, we got this a little larger. On Friday at the open house, it was kind of small, but I think we got to expand it. Okay, nomenclatures of alcohols and ethers. Where's that yardstick? Okay, an alcohol has the OH group, hydroxyl group attached to a carbon, R being some type of carbon. If R is sp3, okay, like a methyl, we're going to call that like an aliphatic or saturated alcohol, referring to the group that's attached. Aliphatic is just an old term for sort of just saturated. The R group can be aromatic. If it's aromatic, it's going to be a phenol. Here's phenol here, with the R group being aromatic. Nothing new there. Enol, that's when the OH is on the alkene, and so it's an enol. Enols are not stable. We saw them in Organic 1 when we hydrated an alkyne, formed an enol, and then it tautomerized to the ketone or so. We will cover enols more precisely during test 4 because they're related to aldehydes ketones. Okay, ethanol would be an example of a primary alcohol. Basically, we're talking about the carbon, okay? Not carbons on the oxygen. If we put another carbon on the oxygen, it's no longer an alcohol. We're talking about the carbon here, bonded to ego. If it has one carbon attached to it, it's primary. If that carbon has 2 attached, it's secondary. If it has 3 attached, it's tertiary. And these are examples. Ethanol, isopropanol, tert-butanol. Oh, that's a T-butyl group, tert-butyl. And then the phenol on the end. Phenols, will largely be when we do aromatics. Phenols have a little bit different chemistry than saturated alcohols. Okay, let's look at nomenclature. How do we name this alcohol here? It's just like with alkanes. We're going to identify the longest continuous chain of carbons, not oxygen, carbons. Longest continuous carbon chain. 1, 2, 3, 4. Okay? There's no choice. 4. So what we got here?
Butanol.
Okay? The butane, but we replace the E with what?
Oh.
Yeah. Okay? Butanol. Now what is this? 1, 2, 3, 4. It's an alcohol, so you call it, you name it as an alcohol, replace it with an OL. It's also butanol, right? These are isomers. We've got to say how this is. But we're going to number these as 1, 2, 3, 4. The carbon nearest the OH is number 1. Numbering begins with N nearest OH, the hydroxyl group. Where's the 1 here?
That's right side.
Is it right there?
No.
No, it's right there because it begins with the N. Begins at an N. That N is closer than the OH than this one. 1, 2, 3, 4. Now you say, where is the hydroxyl group? You put it at the front. That's 1 butanol. Hydroxyl group's at the 1 position. So what is this? 2 butanol. Okay, have different names. Constitutional isomers. Different connectivity. The OH is connected at the 1 position. Here it's connected at the 2. 1 butanol is also called N-butanol. And we can also abbreviate that, sort of like that. But the N means normal, and normal refers to just straight chain. Whereas 2-butanol would be called more of a branched alcohol. Okay, substituents get lowest numbers. That's nothing new. Let's name this alcohol here. Longest continuous chain, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3. Any way you go, it's 5, right? Boom. It doesn't matter which one we include here, it's going to be the same. 5 is what? Pentane, I've got an OH, so this is an alcohol. I mean, the OH is the only functional group. So we name it as an alcohol by replacing the E with an OL. Okay, where's the OH group at?
2.
Okay, that's going to be 1, making that 2. And what else is on this 2-pentanol? Yeah, we have this methyl group. Where is this? It's also at the 2. So we have 2-methyl 2-pentanol. That really doesn't illustrate substitute lowest numbers. Really, the substitute lowest numbers is only going to be relevant if, like, you could go either way with naming the OH. It's almost pretty much, coming from organic 1, it's almost kind of a duh statement. Let's see here. Okay, this is if there were no groups here, what would this be called? Cyclohexane. Okay. Now, chlorine is always just a substituent. Okay, it's never going to. This is an alcohol with a chlorine substituent. Okay, so since it's an alcohol, what do we want to do? Replace the E with OL, cyclohexanol. That right there is cyclohexanol. It's got a chlorine. What position is the chlorine? 3. See, this is 1. See, a ring doesn't have an N. The 1 position is where the OH is. Now, do you want to go 2, 3, 4, 5? No, you want to go 2, 3. Subject's lowest numbers. So this is 3-chloro cyclohexanol. You don't need to put the 1, because just by definition, the OH is at the 1 position, because it's a ring. Okay, there should be nomenclature in your textbook for practice. Let's look at ethers. Ethers, of course, oxygen with 2 R groups. It can be sp3 or sp2. It can be aromatic. It can be alkene. They're all stable. You could call it. You could maybe have something like an enol ether. Ethers could have the same groups on both sides, like 2 alkyls. That would be called a symmetrical ether, diethyl ether. Or they could be non-symmetrical, T-butyl on one side, methyl on the other. That's called methyl terbutyl ether. Used to put it in gasoline, but it got phased out. Now they're putting ethanol in gasoline. Those are put in gasoline to increase the oxygen content, so it'll burn a little bit cleaner. Then you have cyclic ethers, where the oxygen is part of the ring. THF is a common solvent. Let's look at nomenclature. Basically, it's going to be 3 words. You're going to state the 2 groups that are on the oxygen and then say ether. Let's do one using that stuff right there. Okay, first, you see this compound. Again, halogen is just a substituent. You see it's an ether here. Okay? It's going to be 3 words. It's going to be that alphabetical order, plus ether. Well, what is this group over here? Well, let's say 1, 2, 3. How do you do this? Well, you could use a common name, but we're going to do everything IUPAC. Longest continuous chain. Each one is sort of its own independent thing. Longest continuous chain, the 1 position is always connected to the oxygen. That's what it says right here. Closest to the oxygen. Longest continuous chain, that's 2. Either way you go, that's 3. So coming off the oxygen is a what? It's a propyl. 1, 2, 3. What's on the propyl? There's a methyl on the propyl. So that right there is a 2-methyl propyl. YL ending because it's a substituent. Now, that's all, we can also give this a common name. Anybody know a common name of that?
Isopropyl.
No, it's not isopropyl, it's isobutyl. There's 4 carbons total there. Common name is names all 4 together. Okay. Okay, so what is this over here? That's 1, 2, 3, 4. What is that? 4-chlorobutyl. 4-chlorobutyl. It's not butane. Butane would have another H there, just be one molecule, one thing. Here are the 2 things on the oxygen. That's 1 word, that's 2 words. What do you put next? Ether. There you go, there's your name. Is it in alphabetical order? Yes, that's why I put the chlorine over here. Four-chlorobutyl, 2-methylpropyl ether. What do you want to call the one on the right? What is that? Cyclopentane, but it's a substituent, so it's a cyclopentyl. It's a symmetrical. When it's symmetrical, you can just use di. And it's just only 2 words. Dicyclopentyl ether. Back up top. What do you want to call this guy? Diethyl ether. Very common solvent. Usually in lab we just call it ether because it's the most common. What do you want to call the one on the right? Now, T-butyl is a common name. Okay? T-butyl. Now also, they don't know how to put things in alphabetical order because B would become before M. So it should be called T-butyl methyl ether. But somebody thought the T took precedence, and it's too late now. What am I going to call this one down here? So I'm saying methyl, what is this? Benzene ring. What do you call benzene when it's a substituent? Phenyl. Methyl. Phenyl ether. Methyl phenyl ether.
Do you not need the dashes in between?
Those 3 separate words. Nobody calls it this. We will call it anisole. Aromatics, a lot of aromatics go by common names. We'll learn those common names during test 2. And we will call that anisole. Okay, so that's your sort of introductory nomenclature. Again, it should be some practice in the textbook. Okay, chemistry of alcohols. Chemistry of alcohols, chapter 13. The green sheet shows... Green sheet gives a summary of all of test 1 except for NMR. Front and back. At the top, we'll see chemistry of alcohols. With an alcohol, you can do substitution and elimination. We did both of those in Organic 1. You can also do O-alkylation. You can put an alkyl group on the oxygen, turn it into an ether. We actually also did that in Organic 1, right? Called Williamson ether synthesis was. So a lot of that's going to be reviewed. We'll do some new chemistry there, some new reagents. Okay, a lot of review. One new thing is we will oxidize. Alcohols can be oxidized to give like aldehydes or ketones. In case of aldehydes, you can further oxidize them to carboxylic acid. So we'll have to learn about the redox of alcohols. Very important topic of alcohols. One of the labs we'll be doing is a oxidation of a diol. Okay? So there we go. If you look down below, we'll then move on to chemistry of ethers and epoxides. On the back we have, well, there are the alcohol oxidations we'll refer to. Also during test 1 we'll do alkene oxidations. Organic 1 we did alkene sort of addition reactions. There's some other reactions of alkenes, in particular oxidation of alkenes. I think that's it. That's everything other than NMR for test 1. Okay, what's first? Substitution here. Okay? So we move to the blue sheet, and guess what we have, number 1? Substitution. Okay, first thing we need to know is OH is a poor leaving group for rate determining steps. Everybody agree? How do you make OH a better leaving group? Protonate it. We can also convert it to a tosylate, right? Okay. First, let's look at protonating. Reaction with HX to give alkyl halides. Some things there. Nucleophilic strength. Reaction can be either SN1 or SN2. So in Organic 1, we were really looking at the fundamental mechanism. Okay? In Organic 2, we're going to focus more on the transformation. What are we making? What chemistry are we doing? What's the outcome? For example, what are we doing here? We're converting an alcohol to what? Alkyl halide. Okay? Now hopefully I have said what we're doing here. But what I'm trying to get at is you've got to develop some terminology, what we're doing. Because if you know what you're doing, then you know how to do it. If you don't know what you're doing, you don't even know where to start. Okay? How do you typically convert an alcohol to an alkyl halide? You react it with what? What type of acid? HX. It's right there in bold. Okay? What I'm trying to get at is that I don't just write whatever I'm thinking up there. I try to write very strategically, this is what we're doing. Start with that, okay, get that terminology, say, okay, I know how to, okay? And then I write some important things. Here we go, here's an example. Alcohol reacting with HX to make an alkyl halide. But mechanistically, that's what we want to be able to do. It's a substitution reaction because we're substituting the OH for the halide. Okay, you know two substitution mechanisms, SN1 and 2. What is it? SN2. Well, let's see. What's the first step? We can just show that ionized. That's okay. First step, these electrons do what? Okay, every time you use an arrow, you start by saying what?
These electrons.
These electrons. These electrons. These electrons. We don't just start drawing arrows like this. Alright? Every time you start doing an arrow, please say, okay, these electrons. If it's a lone pair, I usually circle them. Protonate the alcohol. You should be able to do this. What's next? OH leaves to make primary cation?
No.
No.
The bromine attacks.
Next step is these electrons back here, kick off the water. What do you get? You get that plus what?
Water.
Plus water. There you go. And the mechanism is what? SN2 with a sort of an activation step to make your leaving group better. Okay? Never make primary cations unless you like have to, or okay? Did we have to, or could we have done SN2? The mechanism here is SN2 because you don't want to make a primary cation. Alright? Now SN2s typically often require a little bit of heat, so in practice you might heat this a little bit, maybe an hour or two. Okay, let's do this one down here. Looks like if I react this alcohol as S with HCl, I get this product. I'm not given any outcome. Let's see if we can predict the outcome, because that is chiral. What do you want to do first? What is the S? That's stereochemistry. RS, chiral carbon. What's the first step?
Protonate oxygen.
Protonate the alcohol. Can I just protonate it without having to do mechanism?
Yeah.
Now on a quiz or test, you need to show that step. I assume everybody can protonate an alcohol. Okay? So we'll probably protonate alcohols about 30 or 40 times this semester, and if I can save that 30 or 40 minutes, that'll be good. Okay? If you want to learn how to protonate alcohol, we did it right there. It's the same thing. H plus, Cl minus. What's next?
Form a carbocation.
Why not attack here? That's a tertiary carbon. You never do SN2 at tertiary carbon, do you?
No.
Right, so don't do that. So what can you do here?
Have a leaving group leave.
Ionization, just have it ionized. Is ionization reasonable? What do you get? You get that, plus what? Or what did we lose?
Water.
Yeah, we lost water, I'll show it like that. We get a carbocation. What's the geometry of the carbocation?
Planar.
Planar, SP2. Trigonal planar. Okay, everything's flat on the board. That's why I didn't draw any dashed or bold anymore. Planar. That forward back is gone. Okay, how do you want to get, can we get final product from here?
Yes.
Now the chlorine does what? These electrons
Both
attack
sides.
carbocation, and that's going to give that product, but what type of stereochemistry? Racemic. Why is it racemic? Because the carbocation right here on the board, planar, the chlorine either attacks from the front or it attacks from the hull side, the back. What does racemic mean? It means we have boom, boom. I mean, you can draw it with the chlorine coming in different ways. I mean, that's where the chlorine came in from the back. And that's where it came in from the front. Now you can draw these in various ways, but basically you want to have R and S. I don't know which is R, which is S. That's what racemic means, right? Question?
Yes, so when you show the leaving group leaving, like, we talked about last semester, but I'm just like trying to remember. So when you show like the arrow of the leaving group leaving, are you supposed to show that like bond going on with the oxygen, or like, because you have like one of them molecules going on, the other one just is going to free space.
Well, I like your clarity there. You can get more precise.
Okay.
I mean, it's okay. It's like, what's the borderline? You'd rather not just do something like this. I mean,
Okay.
there is some precision that goes with your erg movement. yes. Ultimately, WDAM, what does arrow mean? I drew an arrow here, what is this supposed to mean? These two electrons are breaking away from the carbon and going to just become what? A second lone pair on oxygen. And that's going to be an oxygen with now 2 lone pairs and 2 H's. And what do you call that? Water. So you do need to know what your arrow means. And if you're just sending them off into space, well, you're going to end up not doing well at some point. Okay, so stereochemical outcome is racemic. Why? Because it's ultimately what mechanism? Oh, it's SN1. Okay. Here's an alcohol. Now it says HX. It doesn't have to be HX. Ultimately, what do we need to do this chemistry that we're doing? We need H plus, and we need X minus. That is H plus acid, and then the halide minus. Now this could come from HX. HX would supply both. But you can also do this maybe even something like this. What does this supply? H plus. And what does that supply? I minus. Okay? So you got your 2 things you need. It just doesn't come from HI. See, HI is kind of unstable. It's a little bit expensive. In practice, you may use more of the 2 cheaper reagents, but you get the same outcome because you have the 2 reactive species you need there. Okay? I'll let you do this mechanism on your own. Based on, I gave you stereochemical outcome, what's the mechanism? Yeah, this is an SN2. Why? Because I'm showing inversion. SN1 would give racemic. So you can work through that on your own. The one below, this supplies the H plus, that supplies Cl minus. Supply mechanism for homework. Okay? Now I'm not giving you any stereochemistry here. That means you're going to have to use some other knowledge or information to sort of predict mechanism. I also see something odd about this one because here the OH is on the carbon. The chlorine is not on that carbon. So what happened? It's like a rearrangement. What type of chemistry do you get rearrangements with? Carbocation chemistry. See? There you go. Please look at those 2. There will be a number of chemical tests throughout the semester. Okay? A little bit old-fashioned, a little bit outdated. I like them because they reinforce the chemistry and the mechanisms. Okay? Also, a little bit of practical knowledge. Lucas test. Lucas test tells you what type of alcohol do you have. That is it primary, secondary, or tertiary? It's not written here, but you react the alcohol with, it's on the other page. Let's just flip over. You react the alcohol with HCl. Which also includes zinc chloride. It's a Lewis acid. It makes it more acidic. Makes it react a little bit faster. Not always. It may not actually need to be included, but this is called the Lucas reagent. HCl, zinc chloride. We'll talk about mechanism a little bit more. It's tertiary, secondary, primary. Reacting mechanism here is SN1, listed on the flip side. Okay, SN1. Which one of these is going to undergo SN1 the fastest? Tertiary. So you protonate this, and you're looking for it to ionize, SN1. Cation, that will be fastest. If you react this with these reagents, in terms of the chemistry, you can almost ignore the zinc chloride. Okay? But you see ACl, what are we going to get? Alcohol gets converted to alkyl chloride. Operating mechanism, again, SN1. It's going to be faster. The chemical test part is you're looking for a water-insoluble product that will separate. Now this is aqueous. This product is no longer water-soluble. What you're looking at, how fast does it take to get a second layer? That is, for this to form and make a second layer. If it's tertiary, it's going to be almost instant. In fact, in organic 1, didn't we react like T-amyl alcohol with ACl? Shaken, not stirred? We did it in a subfunnel because it's so fast, as soon as you mix them, it's done. So it's like, let's mix them here and then pour it in the subfunnel. That's just a waste of time. So we just mixed in the subfunnel. It was almost instantaneous because it was tertiary. If you have a secondary, you try to do this, it's going to take 5 or 10 minutes. That is, it won't be instantaneous. It'll be a little bit sluggish. But it will occur because a secondary cation is doable. If you've got a primary alcohol, well, you might as well keep waiting. The reaction will never occur. It would be just super slow. Okay? Basically, you're looking for how long does it take for the layer to form. Question?
So, in the case of the third one, with the primary alcohol, why can't that just do an essence?
Because, well, good point. I told you the operating mechanism is SN1.
Yeah.
The question is, okay, valid question. SN2s typically require heat. Okay? You're doing this at room temperature, and it's just not enough heat for the SN2 to take place. Good question. Okay. I pretty much just told you that SN1 is the operating mechanism. Great question. Okay. That's one of the major reactions of alcohols, is converting them to alkyl halides. Mostly review, yeah? We'll see some other ways to do it a little bit later. Next on the outline is tosylates. This is another way to make the OH a good leaving group. So this is organic 1. Take an alcohol reacting with tosyl chloride, some type of weak base like pyridine. You get your O-tosyl. This portion is called your tosyl. And it is a good leaving group. That's toluene sulfonyl. That's how you get the tosyl. You don't have to have acid to protonate the oxygen. It'll leave without acid. Then you could come in with a strong nucleophile, something like this maybe, and these electrons attack here and kick off the oxygen, kick off the tosylate. SN2. No acid required. Didn't Phil Collins have a album back in the 80s, no acid required? Y'all think about it. Tosylate. There are variations of tosylate. I mentioned these in organic 1. Methylate. That's where the benign group coming off the sulfur is just a methyl. Triflate. That's a trifluoromethyl. It's actually very good. Okay. It's just at the introductory level, the only one you'll see in a textbook is the tosylate. We'll also mention these down here. I think we'll actually be using diethyl sulfate here in lab. Our first lab next week is alkylation of Tylenol, acetaminophen, to make phenacetin. These guys are very similar. If you just ignore one side, it's actually sort of a repeat over there because it's symmetrical. This side looks like this, yeah? And so nucleophile, you come in, kick that off, and so this serves sort of as an ethyl source. These are very cheap. Instead of ethyls on each oxygen, if that was H's on each oxygen, what would that molecule be?
Sulfuric acid.
Be sulfuric acid. See, these are kind of esters of sulfuric acid, and they're very cheap. They're commonly used to supply methyl groups or ethyl groups for like SN2. They're somewhat analogous to this. Typically, only one side reacts, although theoretically you can react over here and kick that off too. These are also pretty darn toxic, because usually potent alkylating agents tend to be toxic, alkylate your DNA. Okay, what we need to do here, I didn't do it in Organic 1, is we need to show mechanism. We need to show mechanism here. Hey guys. Hey guys. First off, tosyl chloride would just be a chlorine here. This is generic for the aromatic group. Okay, this is just the phenyl methyl. Pyridine, benzene ring, 1 nitrogen, lone pair, sp2 nitrogen, slightly basic. So this reacts with this in the presence of pyridine to give this. Obviously, the O replaces the chlorine. So under my hand it used to be a chlorine. Now it's the O-propyl. Please do that mechanism. Okay. Very importantly, we're going to learn something for that mechanism. That will be very important throughout the entire course. Please get your lab manual and be ready to check in this week. See you Wednesday.